Okay, so let's get started. So I will hand out the exams at the end of the class. And generally people have done well. The average is 84.5, which is actually quite good. Actually higher than historical average. So the exam was somewhat straightforward. People did well. The grading was very lenient. So all three factors have contributed to a pretty good average score. So I think people have generally done well. Take a look at your exam after I hand it out. The solution should be posted soon. They are not up on Moodle. The sample solutions. Compare your answers with the sample solution. If you have questions, come talk to me. Okay? Don't go to the TA because the TA was not involved in the grading of the exam. Okay, so I will deal with your exam questions. Right? So with that, let's get started. We were talking about paging last time. So this is the picture to keep in mind. So what we have done is gone from a contiguous memory allocation scheme where processes get arbitrary sized chunks of memory, okay, which creates fragmentation. So we went from that approach to an approach where you take RAM, you partition it into fixed size chunks called frames. You take a process, you partition it into the same fixed size chunks called pages, and you can assign any page of a process to any location in memory. There's no requirement that the process be contiguously laid out anymore. That gets rid of external fragmentation. Okay, so the only thing that you have to keep in mind is there is still going to be some internal fragmentation. Okay, there's no external fragmentation in paging, but there's internal fragmentation, and if you remember, internal fragmentation is a problem where the process gets a little more memory than it asked for and you waste that little more. Okay, in the context of contiguous allocation, he said if rather than having a tiny hole, you just give it a little more and avoid that hole. So the question is, why does paging have internal fragmentation and what is the amount of internal fragmentation? Yes?
It can have internal fragmentation because each page is a specific size, so if it only needs like half of that, let's say, then the other half is just wasted.
Okay. So that's exactly right. The reason you have internal fragmentation is process size can be arbitrary. Okay, you cannot mandate that the process size is some multiple of pages. Okay, it could be of any size. So when a process starts up and requests a certain amount of memory, you have to basically allocate it a certain number of pages, so you're going to round it up to the next page size. If you ask for, let's say, 2 3/4 pages, you are going to actually allocate 3 pages. So you're going to waste a little bit of memory because you can't allocate anything smaller than a page. Okay, and you'll assume that process sizes are arbitrary. So when the process starts up, you take its size, you round it to the next page size, and then allocate that. Okay? So that begs the question: what is the amount of internal fragmentation you're typically going to see? What is the average amount of space you're going to waste in paging? Yes.
Depends on how large your programs are.
It depends on how large the programs are. Okay. So we are going to assume that you will basically get an integral number of pages. You ask for some size, you round it up. So if it's 100.6 pages, you will give it 101 pages. Okay. So what should be clear is it actually doesn't depend on the size of the process. You're only wasting space in the last page of the process. Okay, so that's the first point. And the question is, how much space will you waste?
So the fewer pages you have, the more space you waste, right?
Okay, fewer pages you have, the more space you waste. Why is that?
Well, if you add one page, then you only get one process in it. Basically all the memory will be wasted. But if pages were as small as like individual bytes, then basically every single.
So you are saying that the page size actually governs internal fragmentation. That is true as well. But let's assume you are given a page size P. The question is, how much space are you going to waste per process? Yes?
Half a page.
Okay, so on an average, you are going to waste half a page. So the last page, you are going to waste something. Right? For every process, the last page. So some processes may basically only request a quarter of a page in the last page and you wasted 3/4. Others may request more. So on an average, if you look at processes, you're going to waste half a page per process. Okay? So in every process, you're going to have internal fragmentation in its last stage, and you're going to waste half a page. That's something I forgot to mention last time, so I didn't want to mention it again. This is the picture again to keep in mind. CPU is executing a process, it's generating virtual addresses. Virtual addresses are simply integers. Here we said because we are restricting the page size to be some exponent of 2, we also limit the number of pages in memory to be some exponent of 2, rather than doing some complicated arithmetic, not quite complicated, doing a division and mod. You can simply look at the most significant bits and the least significant bits, and that's going to give you the page number and an offset within the page. Look at the page number indexed into the page table. That tells you where that page is stored in memory. Okay, that's the frame number. So you translated the page number and an offset to a frame number and an offset. Okay, so that was what we discussed last time, and we are going to continue from that point on. We'll talk a little bit about what happens when a process starts up, what happens when you have context. Okay, I mentioned this briefly, but let's talk about that again. Okay, so let's say new process comes in, it asks for k pages. Okay, now we no longer need these k pages to be contiguous. All we need is to track k unused frames in memory. They could be anywhere in memory. You just find k such frames and you allocate those frames to pages. Okay, so and then basically you are going to construct a page table that says page 1 is at this location in memory, page 2 is this frame in memory, and so on. That's your page table. Okay, and then when you start up, there is no TLB. You have not started executing. So TLB is this hardware cache, as we mentioned, that is going to store the most frequently accessed page table entries. So you are going to flush the TLB, start with an empty TLB, okay, and then you start the process. As the process executes, it's going to execute memory instructions that access memory. You take the memory address, you do the translation, okay, and then you look in the TLB. If the page table to frame mapping is not in the TLB, you can go to the page table, fetch it, and then put it in the TLB. Okay, so you're going to keep doing this until you have some number of entries in the TLB, and then your process execution is going to get better because all subsequent memory address, not all, but most of the subsequent instructions are going to actually access the TLB to do the translation, not the page table. Okay. So this is basically what happens when a process starts up, and then we look at what happens when you do a context switch. So we already know that when you have a context switch, you are going to save the state of the process that is being switched out and restore the state of the process that's going to execute next. Okay, so we talked about all the registers and so on. Okay. Now in addition, you have to save and restore memory management information, which basically says if the page table is stored in any place other than memory. Okay, if the page table is already in memory, there's nothing to save. But if you keep the page table in register, we discussed that option. Certain hardware CPUs may use that option. So if you have that, then you have to save the page table in the PCB, and you could possibly save a copy of the TLB as well. Okay, so you're going to copy the page table register, you're going to copy the TLB, you're going to clear out the TLB, and you'll take the next process, you're going to load its page tables and its TLB. Okay, so basically, this is the extra memory management information that you have to save and restore during a context. Everything we said before still happens, and these steps have to happen in addition to what we talked about last time. Not last time, but several classes back. Any questions on this? Yes, no question.
What's the table-based register?
Okay, what is the table-based register? So basically, that register is in certain CPUs, you are going to have a register that points to where the page table is in memory. Because you need to figure out where that is in memory. Okay, so what you typically do is, it's in the kernel, it's stored by the kernel, so you basically have a pointer to the start of the page table. You don't need that strictly, but that's there as a performance optimization. You can get to the page table faster. It's just the beginning of the page table. Yes, no question.
So when the TLB doesn't have the page you're looking for, so is it going all the way to that is it going to that register? Is that why it takes longer?
Yeah. So the question is, if the entry is not in the TLB, what happens? Right? So as I was mentioning last time, every time you want to do a translation, you first look at the TLB. If it's the TLB, you're done. If it's not in the TLB, you have to go to the page table. The page table itself is in main memory. It's in the process control block. Okay? This register is simply telling you where in memory it's stored. So if you have a TLB miss, you go to this register and say, where should I go to look for the page table? And this says, go look at this address, that's where the page table begins. Then you go to that address and then you find the entry for that location. So that's what you do. Alright, so there are more complicated schemes which we are not going to talk about here, which are called multi-level page tables or multi-level paging, where you don't have one page table per process. As I said, every process has its own page table, but as processes grow very large, rather than storing very large page table with lots of empty entries, you have what is called multi-level paging that tries to optimize the space that you have for maintaining the page table, and also allows processes to be very large. Okay, so we are going to ignore that scheme in this class, but I just wanted to mention what multi-level paging is. There are more details in the book. If you are interested, go look at it. We won't cover that in the class here. Okay. So last point before we move on to the next scheme is sharing. Okay, if you remember when I talked about contiguous allocation, I said two processes cannot share any memory. Okay, and that is required for protection purposes, where one process cannot access some other process's memory address space. Okay. But there are many legitimate reasons where you want processes to share certain parts of RAM. We talked about shared memory some time ago, where we said two processes may explicitly need to allocate a region that is shared or accessible to both processes. They may be producers and consumers, okay, not threads but processes. So you have to allocate some special region to share. Okay. That's one reason you may share. Another reason you may want to share memory is there may be libraries that your process accesses, and there may be many other processes that access the same library. Okay. Rather than repeatedly loading the same library in many different processes and wasting memory, what you could do is you load the library once in memory and have all the processes shared. The library is a piece of code, so it doesn't change. So all the processes can share it as a read-only region. Okay. And that's another reason why you may want to share memory. In fact, that's a very common reason where you actually share memory across processes, your shared libraries. Okay. Now, what you should realize is once you have paging, it's very easy to share memory. Okay. You can basically share memory across processes using paging. The question is how? Yes.
You just store only that library in a page.
Okay.
Something that every other program that uses the library can access the page.
Okay, so the way to think about this is as follows. So this is, let's say, RAM. Okay, here is, let's say, a shared library. Okay. And let's say for simplicity, we'll assume the shared library is just two pages. Okay. This is process A. Okay, it's page table. This is process B's page table. So to share this library between these two processes, all you need to do is have the page tables of two processes point to the same pages. So the page tables are separate, okay, but the page table entries are pointing to the same pages in memory. And now, because you've done this, both processes can access that region of memory. So the way you are actually going to share memory across processes in paging is through the page table. The page table entries are going to point to the same set of pages, okay, across two processes or more than two, and all of those processes will now have access to that region of memory. Okay, so this makes sharing memory across address spaces or across processes very easy. This is what is often done when you have shared memory or shared libraries. Okay, this could not be done when you had contiguous allocation. It was very difficult to do because base and limit registers prevented you from doing this. Okay, any questions on this? So we are going to continue the discussion and move on to the next scheme. Okay, this is going to be segmentation and segmented paging. So these are actually two distinct schemes that actually will build on what you have learned so far. Okay? So what is segmentation? So let's now take a step back and see what we have done as far as memory allocation goes. Okay, so now, if you look at paging, what we are going to call pure paging, we have a process. Okay, and this is, we will call it the OS view of the process. So as far as the OS is concerned, a process is a collection of pages. Okay, there's no structure to the process. It is simply a list or collection of pages. So you have pages, you have page 1, page 0, page 1, page 2, page 3, page n, and so on. So this is how the OS views the process. Okay, it has a page table, of course, that points to where these pages are actually going to be stored in memory and so on. But the OS doesn't actually interpret what is in the page. Okay, it's a page, it's a region of memory, it's of its size, it doesn't care. Okay? This is the OS's view as far as paging is concerned. Okay? But now if you look at the compiler's view of the process, on how actually processes were laid out, if you remember, I have shown a different picture previously where I said a process, okay, has multiple segments. You can have a code segment, you can have the stack segment. You said stack goes down, and then you can have a heap segment. You can, of course, have many other segments to do synchronization, shared library, and so on. Okay? So this is the compiler's view of the process. Okay, this is also our. Okay? And you'll see that these are completely different. OS doesn't care what's in the process. The compiler doesn't care about paging at all. It looks at, okay, here is where the assembly code of the process is. Here is where the stack is stored. This is where the heap is stored, and so on and so forth. Okay? So, since the two don't match up, we can ask a different question. Say, if you have this view of a process, can you actually allocate memory that maps better to this view of the process rather than not looking at what is inside the process and simply allocating memory as a collection of pages? Okay, so we are now going to look at a different scheme called segmentation that is going to try to adapt to this view of the process, the compiler's view of the process. Yeah, so that's basically what segmentation means, and we'll see how this is done. Okay. So what we are going to do in segmentation is assume that a process is some number of segments. There will at least be 3 segments in every process. In most cases, there will be more than 3. Okay, the 3 segments are the code, the stack, and the heap segment. Okay, so when a process starts up, we are going to say that the OS is going to allocate some memory for the code segment, some memory for the stack segment, and some memory for the heap segment. And since the segments are somewhat independent of one another as far as the compiler's view is concerned, you can allocate memory for each of them independently. Okay, so if you have n segments, process is given n chunks of memory. Okay, each segment we'll assume for now is contiguously laid out. Okay, so if this is your process view, the way it will get laid out in RAM is you'll basically map this to some region of memory, that's your code segment. You'll map the stack to some other region of memory, contiguous, that's the stack. And then you'll take the heap and also map it to some other region. Okay, so you're going to allocate memory contiguously in this case, and for each segment that belongs to the process, you'll allocate a contiguous chunk. Okay? So now when the compiler says, go to the stack segment and take the 10th byte of the stack segment, you'll actually look at the beginning of the stack segment and index that byte offset within that segment, and you'll get the address you want to access. Or you say get the next instruction, it is the nth byte of the code segment. Okay, the instructions are all in the code segment. You will actually go to the start of the code segment and look for the nth byte and access that byte. Okay? So this is basically how segmentation is going to work. Okay, so each segment is now a contiguous chunk of memory that has been allocated to that process. Okay, now because each segment is contiguous, you need a base and a limit register for each segment. Okay, just as in dynamic relocation, we allocated one big chunk for the entire process and we had one base and one limit register. Now we assume that the process is partitioned into n segments. Each segment could be of arbitrary size. And for each of those segments, we are going to have a base and limit register. Okay? Yes, you have a question.
I was wondering, when we map the process to RAM, do we keep the same distance between the stack section and the heap section? or if there's
Okay. The
not.
question is, you keep the same distance, you don't have to keep that distance, you just say, this is the largest size of the stack, so you can allocate that for space. So you don't have to be able to do that at all. You can decide how large the stack segment is independently of the heap segment. Okay. So, coming back to how this is going to be laid out. So for each segment, you're going to have base and limit register. So let's say this is the code segment. The base register says this is the start address of the code segment. That's that. The limit register is saying that's the ending address. Okay, so that's what you put there. Okay, then you look at the stack segment, you say what's the starting address, you put that address in the base register, you put the ending address in the limit register, and so on. Okay. So what the compiler is now going to do is simply say, go to segment I and this offset. Okay, so if we want to access an instruction, you say go to segment 0 and this offset. Okay, that's it. So you basically look at this, what is called a segment table now. Okay, we just touched on a page table. This data structure is called a segment table. You are going to go look at the segment table and look for whatever segment you are trying to access. You look at the base register and you take the base register and the offset and you add the two, just as you did in dynamic relocation. Okay, you have the starting address, you have an offset, you sum the two, you get a physical address. Okay, that's exactly what that logic is doing for each segment. Okay, whatever you did for dynamic relocation. Okay, is that clear? So it goes without saying that you need hardware support for base and limit registers. Should also be clear that since you're talking about base and limit registers, segment tables are stored in registers typically. Okay, that's one way to implement segment tables. When we had page tables, you could have very large number of pages. You didn't have enough registers to store the address of each page. So you stored it in a page table which was kept in memory and you had a TLB. Okay? You're not going to have 10,000 segments. Okay? You may have maybe a dozen segments, 2 dozen segments, some small number of segments. Okay? So there you can store the base and limit registers, base and limit addresses in registers if you want. Okay? That's going to help us keep the performance of segmentation good. Okay, so you don't have to deal with going to memory and so on. Okay, so now you can probably imagine that because you have started allocating memory contiguously again, okay, you are going to go back to the problem of external fragmentation. Okay, segments can be of arbitrary size. We said segments are laid out contiguously. Okay, so there's another process that has a code segment that's going to be stored contiguously and so on. As processes come and go, there will be holes in memory. Holes are going to give rise to external fragmentation. Okay, so if you actually have what is called a pure segmentation scheme, you are going to again incur the issue of external fragmentation. Of course, there's going to be internal fragmentation as well. Okay, is that clear? So the good thing about segmentation is it maps nicely to the actual view of the process, which is that it's collection of segments. You allocate memory to each segment. So all that is good. Okay, you can also store the segment table, which is a data structure in registers. So the translation from physical to the virtual to physical addresses is going to be fast. Okay, you don't need a TLB or anything like that yet. Okay, so all of that is good. The downside, of course, is contiguous memory allocation. You have all of the problems we talked about, namely your external fragmentation. If the stack grows and the heap grows as it will, as the process executes, if there's something else stored next to it, you can't grow it anymore. Then you have to move it somewhere else. That's expensive. Okay, so growth of segments is going to be a problem if you don't have enough unused space. If there isn't a hole that is between two segments, you can't accommodate growth. Okay, so all of these problems are going to be bad. So then the question is, paging has the issue of not really mapping into the compiler's view. It's simply an uninterpreted sequence of pages. Okay, you don't actually map it into anything what the process looks like. This is the OS view, okay, but it doesn't have external fragmentation. That view maps nicely into what the process actually does, but if you allocate memory that way, you're going to have fragmentation again. So what can we do to address that problem? Yes.
Break segments into like small pages.
Okay, so look at page segments. Any other suggestions? Yes.
Sorry, but what is the limit of paging?
What is the limit? What is the limit?
What's the limit of paging? Okay.
Meaning limitation or limit?
Limitations.
So there's no limitation as such. All we said is it is not actually looking at what the process actually looks like to a compiler or to a user. Namely, it's a collection of segments. It is simply allocating memory blindly to a process. Just chopping up it into pieces. That's what it looks like. So you want to somehow adapt to that because in some sense the compiler addresses actually say go into this segment and go into this offset and so on. This is how you deal with the execution of a process. For security reasons, code segments are made read-only. Okay, so you can't overwrite your code and inject viruses and so on. Stack segment, because the data is read-write, so you have to do all of that. That's what the compiler does. It's hard to do if that structure is missing from the process layer. Okay, so we will do try. That's why we want to go back to that view and somehow do something about it. Okay, so one suggestion was if you don't want to allocate memory contiguously, you treat each segment as a small process of arbitrary size and you page it. Okay, so that's one approach that you can use that will get rid of external fragments. Any other thoughts here? Okay, so we are going to actually look at this approach that was just suggested, which is called segmented paging. Okay, so now our scheme is going to get more complicated, okay, because your segments, your paging, okay, and you have to combine all of them. So you'll have segment tables, you'll have page tables, okay, so you will have to keep quite a few data structures to track a process. Okay, so the way we are going to go about it is we'll start with the compilers. We like this view because this is the way processes are actually laid out and this is how they execute. Okay, but we are going to say each segment is of arbitrary size. Code, you know, any amount of code. Your stack could be of any size, depends on what variables you have and so on. And we are going to chop each of these into pages. Okay. And then we are going to allocate pages of a segment into memory. Okay, yes, your question.
I have a question about this one.
Okay.
The first bullet, I was wondering why the upper order bits have to be present.
Okay. Question is why does the upper order bit have to be a segment number? So that was the picture I put up here. So because you have these segments, okay, so we are back to segmentation. Each segment is stored contiguously in memory. Okay. So the way you are going to address is you are going to say go into this segment, which is my stack. You say go to the stack, look at the 10th byte. Go to the heap, look at the 15th byte. Go to the code, get the 100th byte. This is how you are going to address it. Because each of them is stored separately. You can't say go get the 50th byte from the beginning. That doesn't make sense because the 50th byte, if that is in the stack segment is somewhere else. It's not laid out contiguously. So you always have to point to a segment and then mention the offset relative to the start of the segment. Okay, so the way you are going to do is you number segments. Segments will go 1 through n. So you generate a segment number and an offset within that segment. So if the code segment is segment 0, you will say segment 0, 100 byte. That will be the 100 byte of the code segment. Okay, is that clear? When you had contiguous allocation, you could just address the entire process just from relative to the start of that process. Okay? Now you can no longer do that because part of the process is no longer contiguous. Okay? So this byte here is not going to be the nth byte relative to the start because this chunk is stored separately from the previous chunk. Okay? So you cannot do that. You have to address the process relative to the start of each segment, not relative to the start of the process itself. So you will have to generate, that is what that first bullet said, you have to generate for every virtual address a segment ID. Okay? Which segment are you trying to address, and then what is the offset within that segment. That's really what we are doing here. Okay, so that's what it says. You have to generate virtual addresses whose upper order bits are segment numbers. So this is basically the picture that I was going to draw here. Easier to just show that. So you have a process with different segments. This is a code segment, there's a heap segment, there's a stack segment. You see that each segment is of arbitrary size because you don't want external fragmentation. You are going to partition each of the segment into fixed size pages, okay, and then take those pages and map them to frames in memory. Okay, so you're going to now have a segment view, but also while you allocate memory for each segment, you're going to use a paging based allocation. Okay, so this is going to get rid of external fragmentation, but it's going to make our memory management more complicated, as we'll see. Okay, so this is basically what the picture is going to look like. So when you try to address a particular byte within your process, first you have to specify which segment is it. Is it in the code segment? Is it in the heap segment, stack segment? We are going to basically number the segment, so you'll have a segment ID. Okay, that's the first part of the address. Okay, that's S in this address. Okay, that's the address, it has three parts. So you have the segment number, which is the first part. Once you have figured out the segment number, you have an offset within the segment. Okay, and the offset is specified as a page number and an offset within the page, because each segment is paged. Right, so if you look at the previous picture here, each of these segments is paged. So you will say segment 1, which may be the heap. Okay? Then you will say page 3 within the heap and offset I within it. Okay, so you have three parts to the address. You first identify the segment. Then you identify which page within the segment you are trying to access, and then which offset within that page. Is that clear? Yes? Because there's an example coming up soon, which you will have to tell me how to do. Okay, so there are three parts. Okay, as we'll see. So we'll have a segment number, a page number, page within the segment, and an offset within the page. And now we have to keep multiple data structures in order to make this work. First, you're going to have a segment table. Okay. Now, the segment table is going to have base and limit registers, but a segment table is not going to actually point to the memory for the segment. It will actually point to the page table for the segment. Okay. Within the segment table, you say where is the page table for the segment. So it goes without saying that now you have multiple page tables for processes. You need a page table for each of these segments. There's a page table for the code segment, the page table for the heap segment, page table for the stack segment. Each is an independent page table. There's one page table or segment table for the process, and then one page table for each segment within the process. Okay, so you'll have lots of page tables, one for each of those segments. Okay, so the way it works is you are going to start with the segment ID. Okay, and then you are going to look at the segment table. Segment table is going to tell you where is the page table stored. And then you go to the page table for that segment. You take the page number, you index into the page table. That's going to tell you the actual frame where the page is stored. Okay, two levels of interaction. Okay, go to the segment table to find the page table. Go to the page table to find the frame. Okay, yes.
So is the idea that the page tables are stored contiguously and the check against a limit register is happening on the memory for the page table?
Yes. So in this case, so that's a very good point. I didn't actually come to this trap here. So we are going to again assume that the page table is going to be stored in memory. So I didn't actually go into where all of these things are stored. So this segment table you can store in registers. That's very fast to access. Okay? Page tables could be large. You don't have enough registers. So like before, we are going to have page tables that's stored in memory. Okay? Kernel is going to store it in the PCB. You can simply assume it's an array in RAM. Okay? Arrays are continuous. So when you have a certain page number, you basically just look at the size of the page table and you say if the segment has 10 pages, you are trying to access the 11th page, that's an out of address access. Okay, out of access. So basically you are going to create a trap. So the limit value here is the size of the page table, which effectively captures the size of the segment itself. Okay, is that clear? Yes.
Would you ever have a situation where de-indexed somewhere outside of the page referenced by the page table?
That's a good question. The question is the offset. Let's not worry about the page, but can the offset access something outside the page? Okay, can you specify an offset? If you have a 16-byte page, can you specify an offset that is greater than that and access something that's outside the page? Some people are saying no.
It's used for the offset.
Okay. Yes, you have something to say. Yeah, if you could access something outside the page, you would have to put a check. But we are going to do something more clever. Right? So as was pointed out, you can control how many bits you have for the offset. Okay? If you have 4-bit offset, okay, the only offsets you can generate are 0 to 2 to the power 4 minus 1. Okay, so you basically say I have 32 byte pages. Okay, I can address that in 5 bits, so I only store 5 bits for the address. So now I cannot even generate an offset that's greater than the maximum size of a page. Okay, so there's no need to put any check because I restricted the address such that I cannot even generate a number that's greater than the maximum size of the page itself. Okay, so that's going to avoid the problem altogether. Okay. Now notice that you can't do that for the page table itself because the number of pages can be of arbitrary size. There is some max, but typically a process may not actually use the max. Okay, so you may have a much smaller page table, so you have to have a limiter. Okay, but pages are of fixed size, so you don't need to actually worry about generating an offset that is greater than the size of the page. Okay, you don't have enough bits to do that, yes.
So the basing limit in segment table is in virtual memory?
Okay, question is the segment table in virtual memory? So we didn't talk about the implementation aspects yet, but broadly speaking, this is what is going to happen. There are a small number of segments in a process. In that process I showed you there are 5 or 6 segments. Okay? So we are going to keep the segment tables in registers, okay? Because you have typically maybe a dozen, more than a dozen registers, a general purpose register. So segment table, because we want all of this translation to be fast. Okay, if you store everything in memory, you're going to have significant slowdown. Okay, the faster the access or the translation, the better your performance. Okay? So segment table we store in register. That's the fastest piece of memory we have. Okay? Page tables we don't have such luck because page tables would be large. So we are going to keep the page table in memory like before. But we will add a TLB, not shown in this picture. But to access page tables, you are going to keep the TLB. Okay, so most frequently accessed entries of each page table will be in the TLB. So the actual picture is a lot more complicated than that. You have multiple page tables. You have a TLB that shows entries from each of those page tables. Okay, so when you generate that address, you look at the base register, find the page table, okay, and then you'll actually look at the TLB to see is the page actually in there. If the page is in there, you're done. If the page is not, then you go to the page table, fetch the entry, do the translation, and populate it in the TLB. Okay, so now you have many steps to perform. Okay, now it's getting more complicated.
Did you say each page table has a TLB or there's one TLB for the whole process?
Okay. Question is, does each page table have a TLB or is there one for the process? So typically TLB is a piece of hardware. Okay? It is shared by shared by all processes. But when a process runs, it's going to be used by that process alone. So it's going to be shared across page table. You don't have TLB per process. That would be a good luxury to have, but most people don't leave it. It's expensive to put fast pieces of memory. Okay, so the TLB is going to be shared across page tables of that process when that process is running. It's like a hash table. You look for the entry there. If you don't find it, you go out to the actual page table. Yes, question.
Sorry, the page size is decided in a way that the total size of memory is divisible by them. Is that why there's no external fragmentation?
Yeah. So the reason you don't have external fragmentation again is you're essentially using segmentation, but you are paging the segments. Page sizes are fixed, like before. You will have a page size at 2 to the power something. Real machines, you have 4K pages, 4096 bytes or 8K pages. Your memory is also some multiple of some exponent of 2. Okay, so you are going to actually be able to address the bits and do the same thing what you did before. Okay? Any other questions? So let's see if there's an example here somewhere. Okay, so here is a quick example. It's not going to be the full-blown example where you are actually have a segment table and so on. It's simply asking the question saying, let's assume you have 256 word memory. Okay? And we'll assume the page table can index 8 pages. Okay, page table indexes 8 pages, page size is 32 words, and you have maximum 8 segments per process. Okay? So each page can have up to 8 pages and page size is 32 words. Okay, so given that scenario, it's asking several questions. The first question is, how many bits do you need for the physical address in such a system? Yes, so you need 8 bits. To answer this question, you have to ask, when you say how many bits do you need, you have to say what's the largest address I can generate. Okay? You have 256 words. So addresses are going to go from 0 to 255. Largest address you can generate is 255. So then you ask how many bits do I need to generate a number 255 in binary. Okay, that's 8 bits. If you have 8-bit integers, you can go from 0 to 255. Okay, so physical addresses require 8 bits. It's the 8-bit system. Okay. Now next question is, how many bits do you need for a virtual address? Okay, typically until now the physical and virtual addresses are of the same size, they will no longer be. Okay, because our virtual addresses have 3 components. There's a segment number, there's a page number, and there is an offset. Okay, so we can go and ask, so the number of bits you need in the virtual address is the number of bits you need for the segment number, the number of bits you need for the page number, and the number of bits you need for the offset. Okay, so you can go and compute each of those. Okay, so you'll say, I have a page size of 32 words. Okay, so that says the offset can be anywhere from 0 to 31. The largest offset will be 31, okay, within a page. Okay, how many bits do you need for that? You need 5 to the power 5. Okay, so that's 5 bits for the offset. Okay, and now the other two are straightforward. Page table can have maximum of 8 pages. So page numbers are going to go from 0 to 7. Okay, 3 bits. Okay, and we said there are 8 segments. The segment number can go from 0 to 7. So the biggest segment number in generate is 7. It's another 3 bits. So 3 bits for the segment, 3 bits for the page, 5 bits for the offset. Okay, that's 11 bits. Okay, so our virtual addresses are going to be bigger than the physical addresses. Okay, so virtual address is 11 bits, and the 3 extra bits just allow you to access the segment number. Okay, so you are going to generate a larger address, and then each of those bits is going to tell you what's the segment ID, the page number within that segment, and an offset within the page. Okay, so that's going to tell you it's 11 bits. You already did this. You also did this. How many segment table entries you said? 3 and so on. So 3 bits. Okay, is that clear? So you have. So the thing to keep in mind is that's the picture. Okay, so you have. The real picture is here in segmented paging, where process has a collection of segments. This is the compiler's view. We will allocate space to each segment independently. That's what we have done. In pure paging, we did not care about segment. We said your size is X. These are the number of pages to get. We don't do that anymore. We say, what's the size of the code segment? And we give it some number of pages. Okay? Then you ask, what's the size of the heap segment? We give it some number. So each of this is paged independently of other segment. So in some sense, each segment looks like a process did in pure paging. Each of those have their own independent page tables. Okay? So you have a segment table to keep track of page tables, and page tables keep track of pages for that segment. Okay? So 2 levels. So each process will have as many page tables as there are segments. Okay? And then there are, so you'll have more than one of these. And then segment table points to each of the page table. Then you basically do the addressing by first looking for the segment. Then you look for the page table. And then you look for the offset. Or rather, you look for the frame number and the offset generate the physical address. Okay, so that's how addressing is going to be. Yes, question.
So when you go to the segment table,
Yeah.
you compare the limit register what with the
You compare the limit register with the offset within the segment. Okay, that's basically going to tell you whether the number you generated is going to be greater than the size of the page table. Okay, in some sense, you're trying to make sure that your entire size there is not going to be greater than the size of this segment itself, just as you did in dynamic relocation. Okay? So there are 2 ways to do this. You can just compare the size of the page table itself and say you cannot address more than that many pages. Or you can take the page number and an offset that's going to give you this actual byte offset within the segment. You compare that to the limit register. So both of those are going to work. Okay, so you cannot have a page number greater than the size of your page table, or you cannot have a total offset that's greater than the size of the segment. That equivalent things to check in this case. Okay, so now we are actually done with segmented paging. Okay, so coming back to sharing, over the last part here, sharing is now even more simple. You have a lot more flexibility than you had for paging. Okay? Not only can you share individual pages, you can share entire segments. Okay, so that makes our job of sharing much more simpler rather. So what we will do is, as you see here, we showed this earlier, but you can have a shared library. Okay? It could be a Java library, or it could be this libc or libmath or whatever it is. Okay, you put the entire library in a segment. Okay? You page the segment. Okay? But now you don't have to share individual pages, you share the entire segment. So what you will do is, your two processes need the same shared library. Okay, in the segment table, you are going to actually point to the page table for that segment. And you are done. Okay, so this is the page table for the shared library. Okay. In process A, you are going to point here. In process B also, you are going to point there. Okay, so now, since you are actually pointing to the same page table, goes without saying that all the pages within that segment get shared by sharing the entire segment itself. Okay? So you can share entire segment. You can also do what you did in paging, which is share independent pages. Okay? The way you will do that is, within the two page tables, you will point to the same page. If you want to share the entire segment, in the two segment tables, you will point to the same page table. Okay, that's your shared library scenario. If you want to share just one page for whatever reason, you take two processes in the respective code or each segment, you are going to have the same entry pointing to the same frame. So now you share everything. So you have a lot more flexibility here. You can share entire segments, and this is actually how shared libraries are used, where you are going to just share the entire segment altogether. Okay? And then you can share individual pages if you have shared variables of various sorts. Okay, any questions on this? Yes?
In general, I mean, when you go to, like when you're sharing memory just in a paging system, wouldn't it be kind of risky to share a page? Just because, like, you know, it seems like, you know, pages aren't necessarily divided in a logical manner, so there might be some memory you don't want sharing.
That's a good point. So the point is, when you're trying to share a page, it's going to be risky because you may want to share some variable I, but there will be other things in the page. Pages are, let's say, 4K in size. And that's your point. So that's a legitimate point. So when you share memory across processes, of any sort, you've got to be careful. You don't want to expose things that were not intended to be shared. So there are two answers to the question. First of all, it's not trivial to do that. Processes can't set that up themselves. Okay, you have to make a system call. It's a shared memory system call. Tell the OS, go set up this region that's shared. Okay? And even if you want to share maybe 10 bytes, it may allocate an entire page and keep the rest of the page unused so that nothing gets shared inadvertently and so on and so forth. Okay, so you are going to, your processes can't merely say, here's a page, let's share it, and you put it into page. You have to go to the OS, you have to declare a system call saying, I explicitly want the region of memory shared within these two processes, and this is the amount of space I want to allocate. It's going to allocate some integral number of pages. There will be unused space there because you can't put anything else there. That's going to be a problem. So you do this in a careful. And when you do shared libraries, also, you are going to do the same thing. You don't let processes go and change it. So you are going to, the OS is going to mark the entire segment read only. Because it's code, there is no need to change code. Okay, so a process gets access to a shared library, which many other processes are accessing. So you don't get to go and trample it or put some bad code there. Now other processes are going to execute some malicious code. You mark shared libraries as read only, so you can't even modify. You try to modify it, you're going to get a segmentation fault, your process will be terminated. So there are lots of safety things you have to put in place to make sharing work well. Yeah, so that's all an aside, but since the question came up, I thought you should understand. Sharing is a good thing, but it has to come with some caveats. You don't let processes do whatever they want, store whatever they want, and share with them and so on. Okay, any other questions here? Alright, so I'm going to. So we talked about where to put the tables already, so I'm not going to go back to that. So segment tables can be stored in registers. The page table can be stored in main memory with a TLB. Okay. Now there are scenarios where you may not have enough registers. So in that case, the only approach you have is to put both segment table and page tables in main memory and use TLB as a cache for both. Okay. If you cannot store the segment table in registers, so then you have 25 segments. And that will require 50 registers, one base and one limit for each segment. You may not have 50 registers to put all of those entries. There are no registers left for anything else. Okay, so if you have scenarios like that, you can just keep both the segment table and page table in main memory in the process control block and just use TLB as a cache for both of them. Okay, that's your only approach. But if you're a small segment, you can put the segment tables at least in registers. Okay, that's quite fast in terms of access. Okay, so I think we talked about all of these, segmented paging and so on. Yeah, so inverted page tables we won't do right now, we'll come back to it. So just to now recap, before we go on to the next scheme, we have gone through actually 4 different approaches so far. Okay, we started with relocation, which is a contiguous allocation scheme. Entire process gets one big chunk of RAM. Okay, you use base and limit registers to track that region of memory. Okay, disadvantage, as we said, is you get external fragmentation. It's hard for the process to grow and so on, but it's a fairly simple approach. Okay? And then we looked at 3 other approaches: pure segmentation, pure paging, and segmented paging, which combines the 2. Yes, segmentation is what we were talking about today. Is the compiler's view of the process. You take each segment, allocate a contiguous chunk, and you address the segment number and offset within the segment. Okay, so this requires segmented paging, segment tables, and you have still external fragmentation in this approach. Okay. And then we looked at paging, which is the OS's view of the process, okay, where you chop the process up into fixed size pages, allocate pages to frames and whatnot. Okay, so that gets rid of external fragmentation, but it also doesn't preserve the compiler's view of the process. A process consists of segments and whatnot. Okay, so the final approach, which is the approach actually used in both systems. The system is to combine segmentation and paging. It's called segmented paging. So processes have segments. Each segment can give arbitrary size. You partition them into fixed size pages and you page each of those segments separately. Each segment has its own page table. Your segment table to track all of it. Okay, so that's the final approach that we have. Okay, so any questions here before we go on to the next scheme, which is when we demand paging? Yes.
I'm not sure that I understand the first point. When we could allocate as many page tables as we
Okay, so what that is saying is, if you didn't actually mention that. So one point you have to keep in mind is when you allocate the page table in memory. Okay, let's say a new process starts. You have to allocate a page table for the process. How large should it be? Okay, so you could say, I decide what's the maximum size of my process. Maximum size of the process is the size of RAM. As of now, we have assumed that the process has to be resident in RAM. So the maximum process size is equal to the size of RAM and you have your machine. So 2 GB on your machine, you can have 2 GB processes. That's the largest size. Okay? So you can say processes could be up to 2 GB in size. So 2 GB divided by 4K pages is n pages. So I allocate a page table of size n every time a new process starts. Okay? So that in this case the page table is fixed. You always allocate the worst size page table. But what that will do is, if the process typically is much smaller than the worst case, you are going to waste a lot of entries in the page table. They will be empty. Yeah, so if you have fixed size page tables and you have the worst case allocated, you will waste a lot of space. Okay, the other approach then is that you basically let the page tables themselves grow and shrink. Okay, now the kernel has to do extra work where you so think of them as resizable arrays. Okay, if you're Python and so on, you can have arrays that grow and shrink. So page table grows, the process grows, the page table grows with it. Okay? So if you have segmented paging, you can actually have more sophisticated schemes that allow you to let the page table grow, so you don't waste space in the page table. You have a maximum size to which it can grow. Beyond that, you don't let it grow anymore, but you don't always allocate a large page table and base space.
And I mean, why can't we do that in just a normal paging scheme?
Oh, yes, you can do that in normal paging scheme as well. Yeah, so I'm saying that will apply to both of those approaches.
Okay.
It's very simple.
So you said that the page tables would have a maximum size. Is that maximum size ever like purposely set to be less than the maximum number of pages in the system so you can decrease your virtual address size?
I didn't get the last part. Is the maximum size going to be set to what? That's the question.
Is the maximum size ever set to a smaller number of pages than can be held by the system so that you can decrease your virtual address size?
Okay, so the question is the maximum size of a page table going to be set to something smaller than the size of RAM, so you can decrease the address size, the virtual address size. Right? You could certainly do that, right? But as we will see next, we want to go the other way. If we don't want processes to be smaller than RAM, we want you to write processes that could be of arbitrary size. You have 2 GB of RAM, why limit your process to 2 GB? Why can't you start a 4 GB process? Can you make that work? And so, in reality, what's going to happen is the virtual addresses can be far bigger than physical addresses because we are going to limit the restriction that a process has to be even smaller than the size of RAM. We can let an individual process be bigger than RAM. And we are going to see how we do that in just a second. So we will actually make it bigger, not smaller, which means you have to be even more careful you don't waste space in the page tables. Any other question here? Alright, so let us continue and we are going to talk about demand paging. Okay, today it says today, but we only 2 minutes left. So we're just going to talk about it briefly. So the main limitations here are going to, so segmented paging is a good scheme. Okay? It's not going to waste space a whole lot. It preserves the compiler's view of the process. All of that is great. But here are the problems that we want to address. Okay? First of all, we said the entire process has to be in memory at all times. Okay? That is limiting in how many processes you can start at all. Okay? Now, as I mentioned, if you have 2 GB of RAM on your machine, each process is half a gig, you are stuck as soon as you are done with 4 processes or 4 running applications, you are done. If you start a 5th one, you're going to get out of memory because you don't have enough memory. Right? So you don't want that. You want users to start as many processes as you want. In fact, if you look at most machines, it may have 100, 200 active processes at any given point. Okay? That's the first problem you want to relax is you don't want to limit the number of processes or number of concurrent applications you can start up based on the size of RAM. Okay? The second thing you want to relax is you don't want to even limit the size of a process to size of RAM. It goes without saying that the process has to be resident in RAM. The maximum size of a process has to be equal to size of RAM. You can't have a process that's bigger than RAM. Okay? You don't want that restriction either. You want to say, yes, if some user wants to start a gigantic process that exceeds the size of RAM, so be it. You start up that process. You won't tell the user go buy more memory. You started the process, may not run very fast, but that's okay, you let the process run. Okay? So how are you going to do this? Somehow, now if you allow lots of processes to start up and process sizes can be greater than size of RAM, you should realize that not everything is actually going to fit in RAM to begin with. Right? So you have more things than you can actually fit in RAM. So you need some other place to put whatever doesn't fit in RAM. Okay, and that other thing is going to be a disk. So what we will assume is so we'll provide the illusion that you have infinite RAM. Your RAM is no longer a limit on your machine. You may actually have 2 or 4 GB of RAM, but we'll pretend, OS will pretend that it has infinite RAM. And whatever doesn't fit in RAM, it's going to put on disk. Okay? And you'll fetch what you need on demand. Okay? It's not that it's going to sit on disk forever, but as and when you need those parts of the processes or those processes, you'll fetch them into memory. And whatever you don't want to use temporarily, you put them back on. So you're going to keep swapping or what is called paging between disk and memory at different points. So we are going to use disk as a backup for RAM. Okay, so now think of it now, the disk is effectively going to limit the number of processes you can start. And disk space is much larger than RAM space. You may have a terabyte disk. You may have only 8 GB of RAM, 4 GB of RAM. So you can store a lot more on a terabyte disk in terms of processes than you can store in a much smaller RAM. So a disk is going to be a much larger but slower main memory. It's the backup for RAM, so it's analogous to how memory is larger, but and cache, you have caches that store frequently accessed portions. So the way we are going to now deal with memory management is by default, processes are going to reside on disk, not memory. Yeah, until now is that process is actually residing in memory. So by default, a process is on disk, but the active part of a process, we are going to take only that subset of that process and keep it in there. So what the view now is, the RAM has different parts of a process in main memory, and the rest of it is actually on disk. Okay, so since you only have subsets of processes, you can basically have a lot more processes than your RAM. The 90-10 rule applies again. This is where it actually works for us. Okay? 90% of the time, a process accesses 10% of its memory or less. That says you don't need more than 10% of the process space to be actually resident in RAM. Most of the time, it's much less than 10%. Okay?
So what exactly is like main memory as far as, so like this, where is the main memory?
What is the main memory?
Yeah. When you're about to see, because you're saying it's like this,
Yeah.
treat it as main memory.
So I'm going to show you a picture. I think I gave you a picture of the slide as well. So you still have RAM. It's not that we got rid of RAM. Okay, so we have RAM. Okay. And it's limited. And let's say we have a gigantic disk. Okay, much bigger than RAM. Okay, this is where you normally store your files. Okay, but we are also going to use the disk transparently to store processes that are active on your system. Okay. So what we will do is, so let's say that's your file system. So you take a portion of the disk, we are going to call it swap space. Okay. Swap space could be in the file system, it could be its own partition. If you've seen Linux, you'll know that it has a separate partition to store its swap space. So swap space is part of the disk where you're actually storing your processes. That's not where you store your files. That's where you actually store processes that are running that you cannot fit in RAM. Okay? So now basically all of your processes are here. Okay, these are not files, they are actually executing processes. Okay, so the A, B, C, and so on. Okay? And parts of these processes that are active are actually going to be in memory. Okay? They are going to be paged and segmented and all of that, but you'll only have, let's say, n pages of A are going to be here and some n pages of B are going to be here, not the entire process. And as A, B, C execute and they access part pages that are not in RAM, you're going to go to that swap space and fetch it on demand. Okay, so you're going to say, A access this page, it's not in RAM, let me go fetch it. You're going to fetch it, put it in memory, and then start executing the process. Okay, this is how, this is called demand paging. Okay? And now what you have done, this is called virtual memory. You must have heard the term virtual memory many times. So this is physical memory, this is actual memory. Disk is virtual memory, it just looks like a larger amount of physical memory, but it's slower. Okay, so essentially for us now, disk is virtual memory, RAM is physical memory. Okay. Disk is much bigger, so now we are no longer limiting that processes all fit in RAM. We no longer care that the process is as big as RAM. You can put a gigantic process in virtual memory because disk is large. And you only have to take parts of it and actually keep it in RAM to execute it. Don't need all of it to execute it. That's the key point. Okay, to execute a process, you only need part of it in RAM because of the 90-10 rule. That is what is going to work. If you needed the whole process, this would have never worked for us. Okay, so because of the 90-10 rule, okay, demand paging is going to let us assume that we can have bigger processes, lots of processes. So basically, the illusion of an infinite amount of RAM. You can start as many processes as you want. Processes can be as large as you want. Okay? There is a limit, but for most practical purposes, you don't hit the limit. So you can do all of this. Processes can be larger than RAM. You can execute the process, even if not all of it is in RAM, and the more processes you can fit in. Okay? So I'm not going to show you details of the scheme, but all I'm going to show you is if you actually look at most of these so if you look at a typical system, you see all the processes. I don't know if this is even visible, but you can see. Okay, so you see anything there? Okay, so if you look at it here, so you'll see that virtual memory is now, in this case, the amount of virtual memory used is 16 gig, only 8 GB of RAM, and then you'll see that if you add up all of that memory, then you'll see that that adds up to more than RAM. There are some additional parameters you can show saying what fraction of this is actually loaded. Okay, that's not being shown here. But if you configure this, you'll see, or if you run top, you'll see this is the actual size of a process, this is the amount of physical memory allocated. The amount of physical memory allocated is typically smaller than the actual size of the process itself. Okay. So you can just go and look at this on Windows or Linux or Mac just to get a feel for how a process size can be greater than RAM, and the total size of all the processes is much, much greater than RAM, typically. Okay, so now I'm going to